Hey YouTube, it's your boy Kenrick here again, aka the Optometry Prodigy, guys. I am back. Firstly, guys, Happy New Year. I know this will be the first video for this year. Happy New Year to everyone, all the best in this upcoming year. For you guys who didn't know, the laptop was done, guys, but now we're up and running. So the videos are going to come again every Friday, 12 p.m. coming at you guys. Let's go into this first one. We're going into thick lenses. Before, I would have done some optics, and we did light, we did refraction, we did thin lenses in that video, and now in this video we're going into the thick lenses, guys. So let's no sticking, let's get right into it. Okay guys, here we are at thick lenses. So one thing we need to remember from the thin lenses, especially the thickness of those lenses were negligible. We didn't need to take it into consideration because it didn't affect certain calculations, certain distances, image distance, vergences as well, objects and image vergence. It didn't affect it much. However, when we look at thick lenses, the thickness is significant, and if we leave all that in calculations and looking for solutions, we will find errors in our measurements or our determinations. So guys, we need to take into consideration thickness when we're doing thick lenses. And thick lenses, we can deal with them in two ways. So thick lenses, we can deal with them in two ways. One of the ways we deal with thick lenses, or we do our calculations to find our power of the lens or vergences, as I mentioned, we can use what we call the matrix system. And in that system, we use matrices to calculate those different things. So to calculate our image distance, to calculate our object vergence, image vergence, magnification, we can use a matrix system. And using matrices, we solve for those. However, another way we can do it, and that's the one we'll be focusing on in this video, is using the system as a multiple lens system. And I know, guys, it's a new year, but the handwriting is the same. Sorry about that. But we have the multiple lens system. And with this system, what we do, we use the surfaces differently. So in our calculations, we have the anterior surface and the posterior surface of one lens. However, we do our calculations using it as two separate systems. So then we have our anterior surface and our posterior surface, and of course we take into consideration the thickness of that lens, or the distance in between that anterior and posterior surface. As we can see here in the image, we have our object, our image being formed, and VO is what we call our virtual object. The virtual object is that object that is formed from the anterior surface. However, the object is never really formed in terms of it being a reality, because it passes through, the rays passes through the posterior lens. So the image is not necessarily formed. So that's why we call it a virtual object, because then those rays are going to go through this posterior surface and form the real image, or the actual image we are looking at. We always try to remember we have our refractive indices of the lens itself, whether that be crown glass, whether that be polycarbonate, different things or different materials we can use with our lenses. And of course, outside we can have air, water, and all these different refractive indices. And guys, before we go into this, I want you to remember or to recall certain formulas. For example, the power of a lens, n prime over, well, n prime minus n over r. N prime is our refractive index of the material, and n is the refractive index of the outside medium, whether it be water or air. Sometimes it may even be the same thing. Maybe it might be another glass or so. And then all of that is going over r. R is our radius of curvature of the lens. Alright? Another thing we need to remember, guys, our object vergence is n over small l. Small l is our object distance from the lens itself, and then our refractive index of the medium outside. We can also look at our image or vergence, which is capital L prime. This will be n prime over small l prime. And again, this will be the image distance, this will be the index of the refractive media, and well, our image versions. Another thing, when we combine these two, we can get our what we call the vergence relationship, which is the image vergence is equal to the object vergence plus the power of the lens. That's our vergence relationship. One more thing to remember, our magnifications, L prime, L over L prime. So our object vergence over our image vergence, it gives us the magnification of that system. So guys, this is some important things or important formulas to remember as we go into thick lenses. So let's jump into an example to show you how we go about calculating for a thick lens. Let me just line up this here so you can see everything. Okay, so here we have a biconvex lens made of crown glass. It has an anterior radius of curvature of 13 centimeters and a posterior radius of curvature of 8 centimeters. Its thickness is 50 millimeters. The object sits at 28 centimeters in front of the lens. Considering the lens thickness, determine the location of the image in relation to the posterior surface and its magnification. So let's look at this. Let's look at the diagram in terms of what the question is saying. So our first surface, the anterior surface, has a radius of curvature of 13 centimeters. Guys, that's around 0.13 meters. And our posterior radius of curvature, 8 centimeters, which is approximately 0.08 meters. The thickness of the lens is 5 centimeters or 50 millimeters. And the object sits 28 centimeters in front of the lens. So we have minus here because you guys remember anything to the left minus anything to the right plus. Also remember in terms of our surfaces, a convergent system is plus, a divergent system is minus. Signs are very important when we dealing with the optics. So let's jump into the question. The first thing we need to calculate here, guys, is the power of these surfaces. We have our radius of curvature for both, so we can calculate that. And what do we also need? So remember the formula, P is equal to N prime N over R. So the other thing we need besides our radius of curvature is our refractive indices. So do we have that? Yes, we have our A, and then we have 1.52, which is the refractive index of crown glass. So let's jump right into it. So let's go with P1 being the first surface, and for that we have the N prime, which is 1.52 over, well, minus 1, and all of that will go over R, which is 13 centimeters. But guys, when we putting this into the formula, when plugging it in, we need to put it in meters. So we're going with 0.13 meters. And for this, as I said, we have this first surface will be a convergent surface, so we leave it the sign convention. You can leave nothing there, or you can put a plus sign to indicate that it's a converging system. The signs are important. And let's see what we can get here. We have 1.52 minus 1 over 0.13, and that will give us approximately 4 diopters. Again, sign convention is important, so plus 4 diopters. Let's find out for the other surface, or the posterior surface. Let's call it P2. So again, our N, so we're going from inside to outside now. So N, which is 1, then N prime, which is 1.52, all over R, which is 8 centimeters. And remember, guys, this time it's a divergent surface. This posterior surface is going to be divergently light. So we're going to go with minus 0.08. Let's see what we will get here. 1 minus 1.52 minus 0.08. And that gives us plus 6.5 diopters. And these things can be plugged in one time here. So we know we have plus 4 here, plus 4, and then plus 6.5. Both of them is diopters. And the next step, guys, what we can do here, we have our power. Actually, let's go into our object versions. That's the next step right there. We can get our object versions from the distance that we have already. So L is equal to N over L. So we can get N would be 1 over, remember, we're going to plug it in meters, but also remember minus 28 because we're on the left side of the lens. So this will be minus 0.28 centimeters. And when we calculate this, we are going to get minus 3.57 diopters. This is our object versions, guys. And since we have our object versions, we can use this and our power that we have for that first surface to calculate our image versions. And guys, the formula for this, remember again, we just went through it. L prime is equal to L plus P. So when we restructure this, actually we don't need to restructure. We just plug in the values here. We will get for L prime, our image versions, we have minus 3.57 plus our 4 diopters. So plus 4, and that, guys, will give us plus 0.43 diopters. And this is our image versions. Our image versions, we can place this below. So plus 0.43 diopters. Also we can place our object versions above as well. Let's place everything into our diagram. Perfect. And let's go right into what else can we find now. So we have our object versions, image versions for the first surface. So let us find the image location. Where would this image form? The image for this first surface, where would it form? And guys, L prime, as we know, is equal to N prime over small l prime. We want to find small l prime. We already have the image version. So when we restructure the formula, we can put our 1.52 over the image versions, which is at the bottom there, as you can see it, is 0.43 diopters at the bottom of the diagram. 0.43 diopters. And when we plug that in, 1.52 plus 0.43, well, over, sorry, 0.43, we will get 3.53. This will be in meters, and this in centimeters is actually 353 centimeters. And guys, now we're going to go into what the posterior surface will give us. But what I want you to remember here is what I was talking about, the virtual object. So this is actually a virtual object. The virtual object is the image formed by the anterior surface. So it forms this image. However, this image is never actually formed because the rays are going to pass through this posterior surface, and therefore this is just an average of where it would drop virtually. So now, guys, we have to see where it will actually form when we consider our thickness of our lens. Remember, we're dealing with thick lenses. We must take into consideration this 5 centimeters. So we need to minus that. So to see where this image will actually form, this virtual object, 353 minus 5 centimeters, that will give us, that will be 348 centimeters. So this is what we can use now to find the image that will be formed in relation to the posterior surface. So guys, basically we're going to go through some of the same steps again. Let me scroll it down a little bit so we can have some more space. So we're going again. Let me change the color here. Okay, so for this posterior surface, the object vergence, again, the formula, L refractive index over object distance, which is our 348. And guys, remember we put in this in terms of meters, so we're going to be so it's going to be 3.48 meters, and this is going to give us let's see here, plus 0.44 diopters. And with this, we can use our divergence relationship, same from above. L prime is equal to L plus P, and we are doing this, guys, to find the image divergence. So our image divergence, we need to use the power 6.5. Remember we calculated that earlier, P2. So we're going object divergence 0.44 plus our power 6.5 diopters, and this is going to give us a total of 6.94 diopters. And plus, because all of this, as you can see, it's a convergent system, we have to keep our signs plus and plus here as well. And the final part for this, guys, we need to find the image location. So this divergence now we can use to find the image location. And similarly as from above, image divergence is equal to the media over image distance. And when we rearrange this formula, we're going to get this. And here we can place our 1.52 over 1.52 over the image divergence. So 6.94. 6.94. And this gives us a total of 0.14 meters, or in other words 14 centimeters. And guys, this is the image location after the posterior surface. So the entire system, when we look at it, when we take into consideration our anterior surface and the image distance that gave us, and then we used it into considering our thickness, and then into the posterior surface, we get our image. Our final image distance is 14 centimeters. And lastly, let's just plug in these values quickly here. So the image divergence for that was, where is it? It's 6.94 diopters. We can place that over here. And also above here as well, we can write in our image divergence, our object divergence, which was 0.44 diopters. Alright, and the last thing they asked us to find was the magnification. And guys, formula for magnification, remember, let's change the color again. Magnification, image divergence over, object divergence over image divergence. So we need to do it for two systems. So we need our image divergence from the first system, minus 3.57, and then our second, and the object divergence from that first system, 0.43, so that's plus 0.43. We need to multiply that by the image divergence over the object divergence. The object divergence divided by the image divergence of that second system. And let's see what we have here. So this first bracket, minus 3.57 over 0.43. That gives us a minus 8.30, and this will be multiplied by plus 0.44 divided by 6.94. That gives us 0.063. When we multiply these two, we get a negative 0.52. And this is times because of magnification. So what this tells us, if you remember from before, is that the image is actually inverted. So it's an inverted image that we have formed. So if we can take a look here now at the diagram, let's take a closer look at the diagram. We can fill in some of these values here. So let's fill in some of the values. So we filled in the power of the lenses, the object divergences, the image divergences. Perhaps let's put in the final image that we got. So the rays coming through the lenses in this direction. Let's say the image falls around here. The final image. Our final image, if you remembered, we got 14 centimeters. So from the posterior surface to the image, it is 14 centimeters. However, if you recall, the image the image location formed by the first surface, the anterior surface, that was actually somewhere around 353 centimeters, and that is the one we call a virtual object. It's not necessarily formed. If we wanted to put that in, it probably would have gone somewhere way out, and that would have been the virtual object. And that would have formed, as this is 14 centimeters, that would have been way out in terms of 353 centimeters away. And guys, that's how we can work using multiple lens system to calculate our divergences, object divergences for image location, object location for our thick lenses. And main thing to note, differentiating it from the thin lenses, we simply take into consideration that change or that thickness, because it is significant in the case of thick lenses. And guys, next time, soon in the future, we'll go through the matrix system. We will use it to calculate these same distances in terms of the image and the object, and even divergences as well, and alongside the magnifications. So guys, I hope you enjoyed this video. I hope you learned something through it. Don't forget to support me on the Facebook and the Instagram pages. I post content there as well. And guys, stay safe out there. I'm out. Peace.